Okay. First, we want to talk about a concept called a probe sequence. Try to determine if the method that can give us good performance or not. So we study the probe sequence to give us some idea if some method works well or not. All right. So when a collision happens, so let's study a typical situation. Yeah. The slot at h of k is not available. So the first time, here, let me draw a diagram. The first time you evaluate your hash function at the given key, h of k, you find that the slot is occupied by another item. So you have to look for some other places. Yeah. So you try another time. Okay? Suppose you have some strategy, some method you can use to find second hash value, but still occupied. You're not lucky. Another collision, another collision, another collision. After many collisions, after many tries, finally, you'll find a vacant slot. So then you can place your data item there. Okay? So that is the typical situation. Yeah. All right. So here you can see you may try many times. Yeah. So we describe that whole procedure. We use a probe sequence to describe that whole long path. Okay? All right. The general information for the sequence of locations. You may try many different locations. Okay? So the first time, that's the try number 0. Okay? Then try number 1, and so on. The last one, try number m-1. Okay? We assume the number of data items n less than or equal to the number of slots n. Okay? No overflow. Okay? Because under this condition, there is no overflow. So sooner or later, when you try this many times, sooner or later, you will find a vacant slot. Okay? Yeah. So you will. Yeah. But how many times? If you're lucky, you only do 1 try. If you're not lucky, you do m try. Okay? So most of the time, you may get some number between 1 and n. Okay? Yeah. So that's the typical procedure description. Yeah. All right. So we call this probe sequence. So we want to study the properties of this probe sequence. All right. What properties do we need for a probe sequence? Yeah. The first one, the sequence should cover all the slots. It should not miss anyone. Otherwise, your hash function is bad. Your hash function design is really bad. It misses some of the slots. So that means those slots can never be used. In that situation, you need to change your hash function. Okay? Yeah. So we can reasonably assume the sequence based on our good hash function design, it can cover all the slots. So that's the first property. Okay. All right. Okay? Yeah. Then let's assume this probe sequence covers all the slots. Then we can understand in this way. It is a permutation of these numbers from 0 through n-1. Because these numbers corresponds to the slot number. So we can understand this way, the slot number. All right. But your probe sequence basically is just a permutation of the slot numbers, m slot numbers, a permutation. Okay? So that's our understanding, the view. Yeah. All right. The simplest probe sequence. Yeah. You may ask how hard to get this property for probe sequence. Not very hard. There is a simple way to get that. That means you use this way. The next try you plus 1, plus 2. Then the last try you plus m minus 1. So you can see this sequence covers all the slots. This sequence, don't forget mod n. This sequence gives a permutation of all your slot numbers. Okay? So it's not very hard. Easiest way to get that property. Yeah. But it may not be a good way. This method is simple, but it may not perform well. That's another issue. The performance may not be good. Yeah. So we can look at that problem, the performance problem. All right. So what problem does this simple design have? Okay, what problem does it have? Yeah. So let's look at this. This probing method is called a linear probing because we use the linear function, linear probing. Okay. All right. So what is the linear probing? So the definition of this method is given this way. We use an auxiliary hash function h prime of k. Okay? So we do not use this function directly, but we need to pick an auxiliary hash function first. Then we will use it to build our, targeting our real hash function in this way. H of two variables, the key, k, the first variable parameter, then the number of tries, I number, the second variable. Okay, so its definition is simple as this: h prime of k, your hash key, plus I mod n. Okay, plus I. Yeah. So here we should understand this way. Put a parenthesis around. Then we mod n at the end. How about that? Yeah. That would be better. Yeah. H prime of k plus I, then mod the slot number n. Yeah. All right. So this is called a linear probing. It is very simple. It satisfies the property we need, but now we need to look at its performance. It has some big problem that will slow down its performance. That problem, we call it primary clustering problem. So what's the primary clustering problem? Let me use a simple diagram to explain it. All right. Suppose we have a hash table. So this is a hash table. Here you can see a block of slots are occupied by existing data items. A block, a cluster. Okay? So it is a cluster of occupied slots. All right. So now we apply our hash function. Okay? So let's do this observation. If a hash function value hits a cluster, okay? So when you evaluate that auxiliary hash function h prime of k, you fall into one of the clusters in the table. Okay? So you hit one. Okay? Then after that, you need to apply the function, your hash function many times, several times, but you need to go through long runs of occupied slots, right? So you need to try another one, try. Then, yeah, remember? Yeah. So to find a vacant slot, you need to go through long runs. That makes your performance very slow. Okay? So this problem we call the primary clustering problem. So the linear probing is not good because of this primary clustering problem. Okay? Yeah. All right. But how to improve it? We don't like it. So how to improve it? Right? Yeah. All right. So the problem is there is another method called quadratic probing. Okay? So we try to improve the problem of linear probing by a new method called quadratic probing. All right. Here, let's look at the diagram another time. The main reason that the linear probing, the primary clustering problem, is so bad in linear probing because the jumping step is too small. Every time we just jump one step, going too slow. Okay? So a direct solution like this, can we increase the jumping step? Can we jump faster? Okay? Faster? Right? Yeah. If we can jump faster, not necessarily one step a time, many steps every time, can we do a little better? Yeah. So we use that idea, increasing the jumping step size. Okay? The jumping step size. Okay? Yeah, we increase that. All right. How do we increase the step size? Okay. This time we use a quadratic function. Quadratic. Okay? We know quadratic function increases faster than linear function. So the quadratic function helps us to jump faster. That's simple. Right? Yeah. So here we still understand in this way. Mod. Okay? Yeah. So now, based on this new design idea, so we have a new property. So every time when we evaluate a number in our probe sequence, we can go faster. Okay? Yeah. All right. But the question is this good enough? Is this one a satisfactory method? Right? Yeah, we want to ask this question. Yeah. There is a problem. The old problem is replaced by a new problem. We solve an old problem. So what is the old problem? We solve the old problem. The old problem is called a primary clustering problem. Clustering. Okay, this problem is solved or partially solved. Okay, yeah, or improved. Yeah, we can say improved, right? Yeah, but there is a new problem. Okay, it is called secondary clustering. Secondary clustering. So an old problem is replaced by a new problem. Okay? Slightly better than the old one, but still not quite good. Okay? What is the secondary clustering? So let me explain the meaning of the second clustering problem. Okay? Although we can jump faster from one cluster to another cluster. Okay, so you get out of one cluster, but you fall into another cluster. So it's still, you need to look for other places. Yeah. So the diagram like this, the first cluster, the second cluster, okay? So you evaluate your hash function value, so you fall into the first cluster, then you jump faster, you fall into another cluster. So this is called secondary clustering problem. So that's still a big negative factor to slow down the overall search performance. So you can see the hash function design is pretty complicated. Okay, so you see people use hashing, but the internal implementation is very difficult. A lot of factors you need to consider. Okay, so how to solve this kind of clustering problem? We need to solve it. We are not satisfied with this solution, secondary clustering. So we don't want to have this secondary clustering problem. Yeah. So we need to find a new solution. Okay. Yeah. So that means linear functions or quadratic functions we use to define our hash function, both not quite good. Okay. Yeah. All right. So we need to try to find a new design to break the pattern. Yeah. So that's that solution, that improved method cannot be covered in our part A, so we have to leave it at part B. So in part B, first we complete that part. Then we learn another new concept, decision tree concept. All right, so let me stop here, and for the whole class for part A.